Hello, this is Dr. Joe Trout from the physics program at the Richard Stockton College of New Jersey. In this lecture, we'll discuss Chapter 10, which is weather systems of the middle latitudes. One of the major weather makers in the middle and high latitudes is the extratropical cyclone. In 1703, Daniel Defoe was the first to propose that storms generally track from the west to the east in the middle latitudes. Our own Ben Franklin in 1743 was the first American to discover that storms usually move in an easterly or northeasterly direction. Also, he observed that the direction of the storm's winds was not an indication of the direction that the storm was moving. So what systems shape the weather of the middle latitudes? We see that the middle latitudes extend from the Tropic of Cancer and Capricorn poleward towards the Arctic and Antarctic circles. This weather is particularly dynamic because of the migration of cyclones and anticyclones, which are embedded in the prevailing westerlies. This chapter examines air masses and fronts and how they're formed and how they begin to die. It also looks at cyclones and anticyclones, and it looks at local and regional circulation systems. So we mentioned the air masses a couple of times before, and an air mass is generally a huge expanse of air covering thousands of square kilometers, and it's relatively uniform horizontally in temperature and humidity. There are abbreviations for the different types of air masses. So we have C, or polar, or warm tropical, or T. We have dry, which is continental, or lowercase c. Humid, which is maritime, or lowercase m. And Arctic, which is a capital A. Air mass source regions have nearly homogeneous surface characteristics over a broad area. So what happens is the air mass stays over a source region for an extended period, and it takes off over on the characteristics of that source region. So here is a map of the North American types and source regions. So you notice we have the Arctic air mass, we have the maritime polar Pacific air masses, we have the maritime polar Atlantic air masses, the continental polar air masses. So with the continental, we expect low humidity, and with the maritime, we expect high humidity. With the Arctic, we expect the cold air mass. We also have a continental tropical air masses, maritime tropical air masses, maritime tropical Gulf masses, and maritime tropical Atlantic air masses. So once again, whenever we see maritime, we expect a high humidity, and whenever we see continental, we expect low humidity. So table 10.1 shows the stability, temperature, and humidity characteristics of the North American air masses. So we start out with the Arctic. It's going to be bitter cold and dry in the winter, and it's going to be stable. We have the continental polar, that's stable in the summer and stable in the winter. Once again, by stability, we're talking about not a lot of vertical mixing. In the winter, it's very cold and dry, and in the summer, it's cool and dry. If we look at the continental tropical, it's unstable in the winter and unstable in the summer, and it's warm and dry in the winter and hot and dry in the summer. The maritime Pacific, or the maritime polar, the Pacific area, is unstable in the summer and winter. In the winter, it's mild and humid, and in the summer, it's mild and humid. The maritime polar on the Atlantic side is unstable in the winter and it's stable in the summer. In both winter and summer, it's cool to cold and humid. We also have the maritime Atlantic. It's unstable in the winter and unstable in the summer. In the winter, it's warm and humid, and in the summer, it's warm and humid. Air masses can be modified, so as air masses eventually move out of their source region, they move to some other region. And as they move, their properties are modified by the surfaces they pass over. So we have air masses are modified, and the air mass modification occurs from things like exchange of heat or moisture, or both, with the surface over which the air mass travels. It can also change its temperature by radiational cooling or heating. We can also have adiabatic heating or cooling associated with large-scale vertical motion. So don't forget, as we move up, if the pressure remains the same or the pressure decreases, we can have our air mass can expand and cool. Or as it moves down, it can be compressed and heated adiabatically. That's without adding or subtracting any heat. So here's some examples. In the winter, as the continental polar air mass travels southward from Canada into the lower 48s, the temperature usually modifies rapidly. By the time it ends up in the southern states, the temperatures will not usually drop much below freezing because the air mass has warmed as it moved over the continent. The sun warms the snow-free ground, and the warmer ground heats the bottom of the air mass, and the heat is then distributed vertically. A similar process of heating and destabilizations occur when a continental polar air mass crosses the east coast and moves over the western Atlantic. The evaporation from the sea surface leads to extensive areas of low clouds and fog. Another example is the continental polar air mass traveling over the snow-covered ground experiences less modification. So much of the incoming solar radiation is reflected rather than being absorbed and re-emitted at a longer wavelength. Some more examples are shown on this slide. We have the tropical air mass modifies less than polar air masses. So they are often warmer than the ground they travel over. So the bottom of the air mass cools and stabilizes it. So for instance, if the bottom is air mass of the bottom of the air mass is cool, if it gets pushed up into the atmosphere, it's more dense than the air surrounding it, and it gets pushed back down. Therefore, there's no convective currents. If a tropical air mass moves over the warmer surface, then the air mass can become even warmer. Air masses undergo significant modifications through orographic uplift. So for example, marine polar air masses sweeping inland from the Pacific Ocean. The rising air cools adiabatically, condensation or deposition occur, and precipitation is triggered on the windward side of slopes. The descent on the leeward side leads to adiabatic warming and cloud dissipation. Therefore, the air mass emerges considerably milder and drier. When two air masses come together, there's a transition zone, and this transition zone is known as a front. And a front is a narrow zone of transition between air masses of different density. So the density differences are usually due to temperature contrast. That's where the name warm front and cold front comes from. The density differences may also be caused by humidity contrast. So the front's transition zone may be 100 plus kilometers. So don't forget, 10 kilometers is about 6 miles. So we're talking about 60 miles long. And a line representing the front on the weather map is drawn along the warm edge of the zone. So a front is always associated with a trough in sea level pressure, so that's a low, and a corresponding wind shift and converging winds. So when the air masses meet at a front, the colder, denser air forces the warmer air to rise. This induces adiabatic cooling, so the warm, moist air rises into the atmosphere and it expands and cools adiabatically, and often cloud and precipitation develop. The slope of the front influences the type of clouds that form, and cold and warm fronts have different slopes associated with them. Normally a warm front is a nice gentle slope, and a cold front is a very severe slope. We also have stationary fronts. So normally when you think of a cold front, you think of cold air coming in replacing warm air. And when you think of a warm front, you think of warm air coming in, or warm air receding and cold air taking its place. Sorry. Normally you think of a cold front, you think of cold air coming in and pushing the warm air out of the way. When you think of a warm front, you think of the cold air receding and the warm air filling in. But a stationary front exhibits essentially no lateral motion. Stationary fronts often happen along the front ridge of the Rocky Mountains when a shallow pool of polar air surges south over the plains and the leading edge is too shallow to cross the mountain. So in essence it gets stuck there and doesn't move, so we don't have the warm air replacing the cold or the cold air replacing the warm. The milder air remains in the Great Basin to the west of the Rockies. A stationary front may also develop when a pre-existent front becomes parallel to the upper level flow pattern or along a boundary in the surface temperature pattern. So typical front slopes from the Earth's surface towards the denser air. It lies in a trough in a pressure pattern, so that's low. Its wind direction changes abruptly across the front. So for example, we could have a cold front that's oriented north-south, and on one side of the front we have a north wind, and on the other side of the front we have a south wind. So the north wind provides the cold air for the cold front, for the cold side of the front, and the southerly winds provide the warm air for the warm side of the front. There may also be a broad region of clouds and precipitation. So here we see a stationary front, and what we normally see is that we have the slope of the front bends over the cold or more dense air. And in this case, we have wind that's blowing up over the cold front, or up over the cold air mass, and clouds will form and we'll get rain or snow. Notice that in a weather map, a stationary front is shown as a mix of the cold front triangles and the little sun for the warm front, and we see that the triangles from the cold front or the cold side point away from the cold side, and the same thing with the warm front. So if you see a pattern like this on a weather map, that's showing you a stationary front. In a warm front, what we see is that the cold air is moving away and the warm air comes in and fills in. The overall characteristics are similar to a stationary front. So as the warm front approaches, the clouds thicken and become lower in altitude. The sequence is cirrus, cirrostratus, altostratus, stratus, nimbostratus, and stratus when the advancing warm air is relatively stable. So the initial cirrus appearance may be more than 620 miles ahead of the front, or about 1,000 kilometers. Just ahead of the front will be steady precipitation, and it usually gives way to drizzle and sometimes frontal fog. If the advancing warm front is unstable, then we have more vigorous uplift can occur and thunderstorms embedded in the overrunning zone. So here we see a warm front, and once again what's happening is the cold air is moving away and the warm air comes in to fill in. We see that the warm front is shown as usually a red line with small suns on it, so red half circles. And they're pointing then in the direction that the front is moving. Here warm air rides up over the cold air, so it's warm, moist air. It expands, it cools, and we have condensation and precipitation forming. In a cold front, the colder, denser air pushes the warm air out of the way. In North America in winter, the temperature contrast along a cold front is usually greater than across a warm or stationary front. In the summer, if we have a cold front, the temperature on either side may actually be about the same. The density contrast arises from the humidity differences. The slope on a cold front is much steeper than the slope on a warm front, so the uplift is confined to a narrow region at or near the cold front's leading edge. If we have warm air that is unstable, then thunderstorms may form and a squall line develop. If the warm air is relatively stable, then nimbostratus and altostratus clouds may form. So here we see the symbol for a cold front. These teeth are supposed to be the biting cold air. The slope is much more extreme. As the cold front comes crashing through, air is pushed up over it. And sometimes we get severe thunderstorms that form at this leading edge. Cold fronts generally trail south or southwesterly from the center of an extratropical cyclone. Backdoor cold fronts move south along the east side of the Appalachian Mountains. We also have something called an occluded front. So normally on this weather stations you listen to, you probably hear about cold, warm, and possibly stationary fronts. You don't hear so much about occluded fronts, but they're very important when talking about cyclones. And typically they form late in a cyclone's life cycle as it moves into the colder air. And what happens is that the faster moving cold front catches up with a warm front. And then it lifts that warm front off of the surface of the earth and produces and lifts it up off the surface of the earth and forms an occluded front. There's three types of occlusions, and they're distinguished by the temperature contrast between the air behind the cold front and the air ahead of the warm front. So we have a cold air occlusion, and that's the air behind the cold front is colder than the cool air ahead of the warm front. And we'll show you pictures of this in a second. It's like a cold front at the surface, but with less air mass contrast. We also have a warm occlusion. Here, air behind the cold front is not as cold as the air ahead of the warm front. And it's like a warm front at the surface. Then we have a neutral occlusion, so there's little difference between the air masses. It's marked by a trough, a wind shift line, and a band of cloudiness and precipitation. So here's what happened. This warm front, shown in red, was actually ahead of the cold front. So we had the cold air was receding and the warm air was replacing it. Behind the warm front, we had a cold front that came crashing through. It was moving much faster than the warm front. It caught up from the warm front and pushed it up off the ground. So for a cold air or a cold type occlusion, we have cold air that was ahead of the warm front and much colder air that was behind the warm front that formed the cold front. So if we look along the ground, we see cold and colder air. These are more common in eastern North America, where the cold air follows behind the front on the northwest winds. With a warm air inclusion, what happens is the air behind the advancing cold front is not as cold as the air ahead of the warm front. So this occurs in northerly portions of the western coast, such as in Europe or the Pacific Northwest, where the marine polar air is behind the cold front. So in this case, what we see is that we have very cold air here, and cold air is following. Once again, the cold front caught up with the warm front and lifted it up off the surface of the earth. So as a summary, we have fronts are characterized based on the movement of the cold air mass. So with a cold front, cold air replaces the warm air. And with a warm front, warm air replaces the cold air. Clouds and precipitation may develop along the front when there is a significant density contrast between the air masses, and there is an adequate supply of water vapor. The properties that define a front are differences in temperature and humidity, wind shift, convergence, and a pressure trough. Frontogenesis is when the front is being formed or grows stronger, and frontolysis is the front weakens. Now we know that extratropical cyclones, also called low pressure systems, and they're major weather makers in the middle and high latitudes. So the winds blow counterclockwise and upward, and the surface winds converge, air rises, expands, and cools, resulting in clouds and precipitation. Their diameter can be 1,000 to 2,000 miles, or 1,500 to 3,000 kilometers. The maximum wind speeds can reach 45 miles an hour. They occur at all seasons, but mostly in the winter, that's December, January, February, and March, in the northern hemisphere. There could be approximately 3 per day poleward of 30 degrees north. They have a lifetime of about 3 to 4 days. The energy source is dynamic forcing, so we have potential to kinetic energy. And they're mostly in the middle latitudes and polar front. Their direction of motion is eastward or northeastward. And their lateral speeds can be 35 to 65 kilometers per hour or 20 to 40 miles per hour. With the isotropical cyclone, what we see is that we have a stationary front that develops a kink and becomes a cold front and a warm front. Eventually this becomes a strong cold front and a strong warm front. Clouds begin to develop. We have a low that's formed. Then the cold air catches up, the cold front catches up with the warm front and pushes it up off the surface. And we have an occluded front that forms. The comma-shaped cloud pattern is characteristic of a well-developed extratropical cyclone where the cold front runs along this comma. So this life cycle that I just talked about is called the Norwegian cyclone model, and this was a conceptual model that originally developed around World War II. It starts with an incipient cyclone, so cyclogenesis, or the birth of a cyclone, usually takes place along the polar front directly under an area of strong horizontal divergence in the upper troposphere. So air pressure at the bottom of the column falls, so we get a low, and a horizontal air pressure gradient develops, and a cyclonic circulation begins. Aloft, the westerlies steers and support the cyclone as it progresses through its life cycle. To the west of the low center, the polar front pushes southeast as a cold front, and east of the low, the polar front advances as a warm front. So next we have B, the wave cyclone, and during this stage the central pressure continues to drop, and the winds strengthen due to an increased pressure gradient. The upper level trough deepens while remaining west of the surface low center. Here we have a warm sector that becomes well defined, and the fronts form a pronounced wave pattern, and a comma cloud is seen in a satellite image. We have extensive stratiform cloudiness appears north of the warm front, and the cyclone moves eastward or northeastward at 45 to 55 kilometers per hour or 25 to 35 miles per hour. Next, the occlusion begins. So the cold front's moving faster than the warm front. It catches up with the warm front and pushes it up off the center. The warm sector area diminishes and the occluded front begins to form. And the upper level pattern shows closed circulation, and it's directly over the surface low. Then something called a dry slot separates the cold front cloud band from the comma-shaped band. The cyclone begins to move slower at approximately 20 miles per hour or 30 kilometers per hour. Finally, we have the bent back occlusion. So now the surface low may become detached from the westerly steering flow, and the occluded front is drawn around the low center. So this warm sector is detached from the cyclone center, and a triple point favors development of a secondary cyclone, and eventually the cyclone weakens. So the entire cycle can occur over several days or a much shorter period. The speed of the development depends on the upper air support. So if we have weak divergence aloft, this will cause a poorly defined system. Sometimes cloudiness and precipitation occur with an upper level or surface trough, which is not associated with a closed system, a closed surface cyclonic circulation. So we don't have that ring of low pressure that forms. So when upper level conditions are ideal, the whole life cycle can occur in less than 36 hours. There's also something called a cyclone bomb, and this in term applied to a rapidly intensifying cyclone and is defined as a central pressure drop of at least 24 millibars in 24 hours. There's few cyclones that ever meet this criteria, and most that do occur in the winter over a warm ocean surface like the Gulf Stream. There's also another model besides the Norwegian model, and this is known as the conveyor belt model. And this is as I said, it's a 3D model, and the steps are discussed previously. This is an alternate 3D model to the steps discussed previously in the Norwegian cyclone model. And this combines horizontal and vertical air motions. And it depicts the circulation in a mature cyclone in terms of three broad interactive systems called conveyor belts. So one thing that was wrong with the Norwegian model is it never adequately explained where all the moisture was coming from to produce all this precipitation. So this model did a better job at doing that, and once again is a conceptual model. So these three conveyor belts which transport air with certain properties from one location to another, and the belts are warm and humid, cold, and dry. So the warm and humid conveyor belt originates in the cyclone's warm sector. It ascends slightly as it flows northward in the warm sector at low levels and then ascends more rapidly over the warm front. And this explains the broad region of clouds and precipitation north of the warm front. The cold conveyor belt originates north of the warm front, and it ascends as it progresses towards the west. This forms the comma cloud and produces the precipitation. It turns clockwise at upper levels and follows a westerly flow aloft. And finally, we have the dry conveyor belt, and this air originates high in the troposphere and low stratosphere, upstream of the upper level trough. And one branch descends southward behind the cold front, and the other forms the dry slot that separates the head and tail of the comma cloud. So here we see the warm conveyor belt bringing up humid warm air, and the cold conveyor belt which swifts up this way, and from aloft we have this dry airstream and the dry conveyor belt. The figure represents an intensifying cyclone in the upper Midwest. First we see how the wind is reacting. So we have a warm front here and a cold front here, and the wind pattern is circulating counterclockwise around the low. So the four sectors are about the low center. So first we have strong air advection in stratiform clouds and non-convective precipitation northwest of the cyclone, or of the low. The cold front south of the low is accompanied by convective precipitation, so sinking and mostly clear skies characterize the southwest sector behind the cold front. The mildest air is in the southeast warm sector of the cyclone, and an extensive overrunning zone is found to the northeast of the low. So notice if we have the low here, what we can see is fog before the warm front. We have drizzle just before the warm front. We have rain on the one side of the warm front. We can have snow on this upper quadrant, and we can have violent thunderstorms as this cold front moves through. If we look here, we have the low. We'll have falling pressure here in the direction of the storm and rising pressure on this side. So as a general rule, the cyclone center moves forward in the same direction at or about 1/2 the speed of the 500 millibar winds. So if we measure the speed at the 500 millibar winds, the speed of the cyclone center is about half of that. The principal storm tracks tend to converge towards the northeast, and the storm tracks appear to originate just east of the Rocky Mountains, but actually form over the Pacific Ocean near Alaska. As the cyclones travel over the mountains, they often lose its identity and reforms over the Great Plains. The nor'easter often intensifies off the North Carolina coast and track towards the northeast along the east coast. So two motions exist: the movement of the cyclone along the coast, and a counterclockwise flow of winds around the storm center, and the winds in the northeast sector of the cyclone blow from the northeast. That's why we're giving the name the nor'easter. Generally, cyclones that form in the south yield more precipitation because they have access to a greater amount of maritime tropical air, which will have a lot of humidity. Cyclogenesis is more frequent in the winter when the mean position of the polar front and jet stream shifts southward. So here we see some principal cyclone tracks and where they form, and most of their paths converge somewhere up around the northeast. If we look at the extratropical cyclones, we see the warm, cold, and warm side. The storm tracks determine the weather at the points on the ground. So if we have track A put Chicago on the warm side with passage of the warm and cold fronts. But track B puts Chicago on the cold side with no frontal passage. So table 10.3 summarizes the general sequence of weather conditions at Chicago. If we look at the winter storms, extratropical cyclones that produce any combination of frozen or freezing precipitation. And an associated hazard is a cold wave, which usually follows the storms. The necessary ingredients for these winter storms include cold air, typically brought by sprawling cold high to the north, and a moisture supply, and an uplift mechanism. So a major storm requires warm and humid air brought northward. The storm moving to the northeast produces the heaviest snow to the north and west of the low center. So it's important to know where this low is going to be, is the track of this low, to see where the snow is going to be the worst. And a blizzard is a severe storm characterized by high winds and reduced visibility due to the falling or blowing snow. So here we see the Colorado track storm system. And we see once again, as this cold front comes in, we could actually get a squall line of thunderstorms. On the back side, on the cold side, we can see snow showers and heavy snow. And here is the track that we're following. And ahead of the warm front, we would see rain. An occluded cyclone is a cold core system, so the lowest temperatures occur in the column just above the surface low. So as the depth of the low increases with altitude, and the cyclone circulation prevails throughout the troposphere and is most intense at high altitudes due to this strong pressure difference across this low that develops. A non-included cyclone is a warm core cyclone, so the lowest temperatures are northwest of the cyclone center, and the highest temperatures are often southeast. So the low aloft is displaced to the cold side of the storm, and the system tilts with altitude. And the upper level low actually lags behind the surface low. as shown in the diagram. These warm core cyclones are stationary and have no fronts, but are generally associated with fair weather. And they form over a broad expanse of humid and semi-arid land in response to intense solar heating of the ground. So the hot surface heats the overlying air and lowers the density of the air column enough for a low to form. And they're usually very shallow. And an anticyclone, a loft, overlies the low. In an anticyclone, subsiding air and diverging surface winds favor formation of a uniform air mass and no fronts in generally fair skies. So we have the Arctic and polar highs. These are cold core anticyclones, and they're labeled either as a polar high, so a continental polar, or an Arctic high, and are products of extreme radiational cooling, often over snow-covered land. So they have a clockwise circulation that weakens with altitude and may even reverse. So usually has a cold trough overlying it, and these exert the highest pressure in the winter. And they're extremely stable with an inversion in the lower kilometer or so. And they interact with the circulation of an extratropical cyclone by helping to maintain and strengthen the temperature contrasts along the cyclone's front. We can also see a warm high, so a warm core anticyclone, and this forms south of the polar front and consists of an extensive area of subsiding warm and dry air. These strengthen with altitude, and examples of these are the Bermuda or Azores high and systems that may develop over the interior of North America, especially in the summer. The greater mass of air over the anticyclone center, related to a higher tropopause, is responsible for the high pressure system. And a cold core anticyclone can become a warm core as it moves southward and modifies. So for anticyclone weather, so we're talking about a high. We have fair weather systems because the surface wind's blowing in a clockwise and outward direction in the northern hemisphere. And they induce subsidence over a broad area. So because of this high pressure, they're going to get divergence at the surface. And the Arctic high produced the lowest temperatures of the winter. And a stalling warm anticyclone can lead to drought and extensive summer heat. There's weak horizontal air pressure gradient over the center can lead to intense nighttime radiational cooling. So ahead of an anticyclone, there may be the strongest northwest winds ushering in polar or Arctic air. And this could bring heavy lake effect snows to the lee side of the lakes. And in summer, the most noticeable effect is not a lowering in temperature, but a lowering in humidity. So since the air is subsiding from aloft, there's not a lot of moisture up there. There's not a moisture source, so you'll see that the humidity will start to lower. So the highs may become entrenched east of the Rockies in the summer and form blocking highs, which will bring high temperatures and eventually droughts result. Then we want to look at the regional circulation systems like sea breezes. What we see with a sea breeze is that the land is going to heat faster than the ocean as the sun beats down on it during the day. That will heat the air just above the surface, which will become more buoyant and move up. And air will blow in from the ocean to fill in, and we'll get this circulation pattern that occurs. So what we see is that we have a pressure of about 110 millibars, and this is the isobar line. And as the isobars follow through, what we see is now we have high pressure here and low pressure inland. So the air will blow from the ocean to the land during the day. At night, the land cools much faster, the ocean remains warm, the air becomes buoyant over the ocean, and the land breeze will come and fill in that vacuum where the buoyant air has risen. And here we get a circulation pattern that at the surface the wind blows off of the land onto the ocean, and aloft that blows from the ocean to the land. A similar circulation pattern forms from mountains. So we have a valley breeze, and what happens is the bare mountain walls absorb solar radiation quickly and heat the surrounding air. So at these walls, this becomes buoyant and moves up the mountain. We can get clouds to form. So if we have two mountain ranges, what we get is subsidence in the center. So the air heats, rises, expands and cools, clouds form, and then subsides. At night what happens is the walls cool faster, so that means we get more dense air that run down the mountain, and we get circulation patterns in the opposite direction. What we can see is fog or low stratus clouds may appear in the valley. We can also end up with Chinook winds, and these are relatively warm and dry winds that develop when air descending over the leeward side slopes of the mountain range is adiabatically compressed. So when air is compressed adiabatically, it begins to warm, and we get strong winds cause stable air in the lowest troposphere to ascend on the windward side. And on the leeward side, stable air descending to the original altitude, and a larger scale of circulation causes further descent. These are also called Santa Ana winds when they're in the southern California. And in this figure, we see a schematic representation of the weather patterns that favors development. And what we have is a high forming here and a strong pressure gradient that brings these Chinook winds. So in Boulder, Colorado, situated in the foothills of the Rocky Mountains, experiences particularly strong and destructive downslope winds. These sometimes gust up to 100 miles per hour or 160 kilometers per hour. And on average, the community sustains about $1 million of damage each year due to these Chinook winds. We also have katabatic winds, and these are driven by gravity. And these are a shallow layer of cold, dense air flows down the hill. and they usually originate in the winter over an extensive snow-covered plateau or highland. The best known katabatic winds are the minstrel and the bora. The minstrel descends from the Alps down the Rhine River valley of the France into the Gulf of Lyons. And bora originates in the high plateau of Croatia and cascades onto the coastal plains along the Adriatic Sea. These are usually weak with speeds less than 10 kilometers per hour. We can also see desert winds form. So as you can imagine, we have hot surfaces, and they may develop superadiabatic lapse rates in the lowest level of the atmosphere. So if you remember, if we had adiabatic lapse rates, we were talking about a drop of 9.8 degrees C per kilometer. And these are highly unstable and generate vigorous upwelling and gusty surface winds, but not much in the way of clouds. And we can have a dust devil, which is a whirling mass of dust-laden air formed by a localized hotspot. So the air is heated and it rises rapidly. Cooler surface air converges on the hotspot, and horizontal wind shear causes the column of rising air to spin around a nearly vertical axis. And dust and debris are picked up, making these visible at altitudes topping 900 meters. Right, so that's about a half a mile. So they may cause damages, as some have winds higher than 75 kilometers per hour or 45 miles per hour. We also see strong thunderstorm downdrafts may generate dust storms known as habab. And here we see some pictures of the dust storms that form and also the dust devil. And it's interesting that these dust devils are so nearly vertical. All right, and that concludes the lecture for Chapter 10.